We're all used to thinking of numbers as just points on a line, right? But what if I told you that's kind of like looking at the world in black and white? Today, we're going to step off that line and into a whole new dimension. And what we find there, well, it reveals some of math's most beautiful secrets. Let's check out the polar perspective of complex numbers.
I mean, really think about it. How many years did you spend in school solving equations? And we were always looking for that one answer, right? The one you could actually point to on a number line. But what happens when you solve for x and poof, the answer just isn't there? Where does it go?
Okay, so take a look at this. It's a pretty simple quadratic equation, and its graph is this nice U-shape, a parabola. But notice something. It never actually touches the x-axis. Now, in school, we're told this means there are no real solutions. But does that make sense? Do the answers just disappear, vanish into thin air? Nope, they didn't vanish at all. They just moved. And to find them, we have to do something kind of radical. We have to expand our whole idea of what a number can even be. Turns out, they're living in another dimension.
And that right there, that's our way in. This is the world of complex numbers. It's a world that isn't stuck on a single boring line. Oh no, it unfolds across a full two-dimensional plane.
So what is a complex number? Well, it's got two parts. You've got the real part, we'll call it A, and that's just a number from the good old number line we all know. But then you've got the imaginary part, B, and that one gets multiplied by this special unit I, which is, get this, the square root of -1.
So how do we even picture this? We use something called the complex plane. Think of it just like a normal graph. The horizontal axis, the x-axis, that's our real axis for the A part. And the vertical axis, the y-axis, that's our imaginary axis for the B part. So any complex number, say a plus bi, can be plotted as a single unique point, AB, on this plane. Simple as that.
All right, so we're in this new landscape. Let's see how things work here. Adding these numbers is super easy. You just add the real parts, then add the imaginary parts. Done. But multiplication? Oh, that's where things get interesting. Okay, so if you want to multiply two complex numbers in this a plus bi format, you have to drag out the old FOIL method from algebra class. First, outer, inner, last. You multiply everything out, you have to remember that I squared is -1, then you have to regroup all the real and imaginary bits. I mean, it works, yeah, but it's clunky. It's a mess. And it gives you zero feeling for what's actually happening on that plane.
So all that algebraic mess just begs the question, right? There has to be a better way, a more elegant, more visual way to think about these points.
And there absolutely is. Let me put it this way. Think about giving someone directions. The old way, the A plus V way, is like saying, okay, go 3 blocks east, then turn and go 4 blocks north. But you could also just say, hey, face that way, northeast, and just walk 5 blocks. See? Both get you to the exact same spot, but the second way is just distance and direction.
And that simple idea, distance and direction, that's the absolute heart of this whole polar perspective. So let's break that down. First up, the distance. It's got a fancy name, the modulus. But all it is the straight line distance from the center, the origin, out to our point. And we figure it out with the good old Pythagorean theorem. It's just a length, always a positive number.
And the direction? That's called the argument. It's just the angle that the line to our point makes with the positive horizontal real axis. We usually call this angle theta.
So what we've got here are two totally different languages to describe the exact same point. On the left, you've got the go east, go north version, the rectangular coordinates, A and B. And on the right, you've got the face this way and walk version, the polar coordinates, R for the distance and theta for the angle.
Now, finding that angle, the argument, can be a little tricky. If you just punch it into a standard calculator, you can get the wrong answer sometimes, depending on which quadrant your point is in. So we use these simple rules to make sure we get the exact right angle every time. It's called the principal argument.
Okay, so you might be thinking, why did we go through all that? Here's why. This is the payoff, because thinking this way in polar form unleashes some seriously incredible power, especially when it's time to multiply.
So here it is. Any complex number can be written out in its polar form. You have r, the distance, multiplied by this combination of cosine theta plus I times sine theta.
Now that cos theta plus I sine theta bit is a mouthful, so mathematicians often just shorten it to cis theta.
Okay, remember that horrible FOIL multiplication from before? Yeah? Okay. Now, forget it. Just throw it away. Because in polar form, the rule is so simple it's almost magical. To multiply two complex numbers, you just multiply their distances and you add their angles. That's it. For example, take 1 plus I times I. With FOIL, you grind it out and get -1 plus I. Okay, but in polar, 1 plus I has a length of √2 and an angle of 45 degrees. I has a length of 1 and an angle of 90 degrees. So, what do? Multiply the lengths. √2 times 1 is √2. Add the angles. 45 plus 90 is 135 degrees. And guess what point has a length of √2 and an angle of 135 degrees? You guessed it, -1 plus I. It's just so much better.
So look what we just did. We took this tedious, ugly algebraic chore and turned it into a simple, beautiful geometric action. Multiplication in the complex plane is just scaling and rotating. That's all it is. You're just stretching it and turning it.
And this idea leads us to the ultimate superpower. It's called de Moivre's theorem. Let's say you need to calculate some complex number to the 10th power. Can you imagine multiplying that thing out 10 times? It would be a nightmare. But with this theorem, you just raise the distance to the 10th power and multiply the angle by 10. Done. It is unbelievably efficient.
So now that we're armed with this new power, we can go back and look at problems that seemed really simple on the surface, but were actually hiding this deep, beautiful structure that we just couldn't see before.
So let's try it out. I'm going to ask you a simple question. What's the cube root of 8? We all know it's 2, right? 2 times 2 times 2 is 8. But is that the only answer?
Well, if you're stuck on the real number line, then yeah, it is. But out here in the complex plane, there are actually three different cube roots of the number 8. And our polar perspective shows us exactly where they are. It's amazing. It turns out that the nth roots of any number are always spaced out perfectly, equally, around a circle. So for the cube roots of 8, that first root is 2, right where we'd expect it on the real axis. But the other two are found by just rotating by 120 degrees, and then another 120 degrees, forming this perfect equilateral triangle. This gorgeous symmetry was completely invisible to us before.
And that just leaves you with this really big question, doesn't it? If a number as basic as 8 can hide this kind of profound geometric beauty just one little dimension away from our number line, it really makes you wonder, what else are we missing? What other elegant, incredible truths are just waiting out there if we only find the right way to look?